Here's some good news. We had a kinetics chapter. It turns out the radioactive decay processes are all first order kinetics. You're not going to have to worry about zero order. You're not going to have to worry about second order. It's all first order. And it comes about when an unstable nuclei decides to fall apart. Spontaneous still does not necessarily mean rapid. Instead, we should think of it as without outside influence. It's going to happen. We're not exactly sure when, but it will happen. Half-life, once again, you already know this, but I'll say it. Time interval in which the number of the radioactive particles is cut in half. So this N is the number of half-lives in an amount of time t when you know what the half-life is. So if you actually had no time, you would have no half-lives, right? If you had exactly a half-life, you'd end up saying, oh, there's one half-life in this amount of time. And we can calculate the fraction that remains. Here are some equations, and they should look reasonably similar. I mean, it's just one of these things that in this chapter, because of the way that physicists write things, they tend to write things this way. How much of the nuclide is there at time t? How much of the nuclide is there when it's time 0? And we were always using concentration at time t and time 0. So it's just a little bit different notation, but it's the same idea that this, if you do it in logs, ends up being a linear process. And k here, this is the natural log of the number 2, the 0.693. So that's what you get. And you might remember them in this format, which is quite similar. Here's the minus kt. If I have logarithm and that's divided, so it's a logarithm of this minus the logarithm of that, well, let's just push that over the other side, and then it won't be minus anymore, it'll be a plus. So this is the other format that we're used to seeing it. And you probably remember finding the half-life from k instead of k from the half-life. But you can see it's the same thing. And that's why I pointed out earlier that the logarithm, natural logarithm of 2, is this 0.693. Now, additionally, we have a situation where instead of talking about the natural log, they realize that it's always a half-life. So they will use 0.5 and raise it to the number of half-lives. And of course, the number of half-lives was the amount of time divided by the half-life. We would say that the amount there was a sub 0, the amount we started with, and then here's a declining exponential. So there's some subtle differences between these, but they're just really notation. It's no different in computation. And we see this pattern, this exponential decay. If we start at time 0 and we have nothing but the red ones, which happen to be radioactive, and then we go 1 half-life, then if we look, we'll find that half of the 40 will end up decaying and turning into the stable product. And if we go another half-life, then the ones that were still red, half of them turn, so 20 goes down to 10. And if we go yet another half-life, well, the 10 will turn into a 5. And this is what we see, the same pattern, a nice decreasing exponential, first order kinetics.